Today, we're diving into something that sounds simple but is actually incredibly complex, figuring out how much sun a place really gets. I mean, this is the kind of science that can make or break a billion-dollar energy project, or, just help you decide if putting solar panels on your own roof is a good idea.
It all really boils down to this one single, super important question. It doesn't matter if you're a homeowner or running a massive power company, this is always square one.
And as you've probably guessed, the answer is a lot more complicated than just saying, well, it's a sunny place. Getting this number right is the difference between a smart investment and a really expensive mistake. So let's look at how the experts actually figure this out.
To get our answer, the first place you'd think to start is with the basics, right? Just pure, predictable math, the beautiful clockwork of our solar system.
We can absolutely 100% calculate the sun's exact path across the sky for any spot on Earth on any day down to the second. It's just geometry. This gives us a theoretical maximum amount of sunshine. But here's the thing. In the real world, these perfect calculations are almost useless because they completely ignore the single biggest wildcard there is, the weather.
Okay, before we go any farther, we got to get two key terms straight, because you'll hear them a lot. First is irradiance. Think of it as the sun's power right now. It's like your car's speedometer. How fast are you going at this exact moment? Then there's insolation. That's the total energy you collect over time, like over a whole day. So if irradiance is your speedometer, insolation is the total distance you've traveled on your trip.
All right, so perfect world math is out. The next logical step seems easy, right? Just measure the actual sunshine for a while and take an average. Simple enough. But this is where things get really, really misleading.
Take a look at this. This data shows the problem perfectly. The average energy here is a solid 5 kilowatt hours per day. Sounds pretty good, right? But look closer. The reality is you have 2 amazing days where you get 8 and 2 pretty awful, cloudy days where you only get 2. You're living in a world of feast or famine.
And that is the whole point. So what if the average is 5? If your home or your factory or whatever needs at least 4 kilowatt hours every single day to run properly, well, that average just failed you half the time. The average completely hides the volatility, and when you're planning for energy, volatility is your worst enemy. So, to solve this problem, scientists and engineers came up with something way smarter, a much more useful tool. They had to find a way to represent a typical year that still captured all that real-world's messiness and variation.
Now, the absolute best, highest quality data you can get comes from these things on the ground called pyranometers. You can think of them as super accurate sunlightometers. They just sit in one place, year after year, sometimes for decades, measuring the sun's radiation every few minutes. They see everything, the perfect days, the cloudy days, the hazy days, building this incredibly rich picture of a place's actual solar climate.
And all that amazing data gets used to build this, a Typical Meteorological Year, or TMY for short. Now, this is not an average. It's more like a greatest hits album, or kind of like a Frankenstein's monster of a year, built by stitching together the most typical, real months from a long history of data.
So here's how they do it. It's pretty clever. Let's say you have 30 years of weather data. You take all 30 Januaries, and you find the one single January that was the most statistically normal of the bunch. You pick that one out. Then you do the same for all 30 Februaries, all 30 Marches, and so on for the whole year. Finally, you stitch those 12 most typical individual months together. What you get is a single, synthetic year of real, hourly data that perfectly captures that location's true personality. The ups, the downs, all of it.
And this TMY data is even smarter, because it breaks sunlight into 2 crucial types. First, you have direct radiation. That's the sunlight that travels in a straight line from the sun and makes a sharp shadow. But then you also have diffuse radiation. That's sunlight that gets scattered by clouds and dust in the atmosphere. It comes at you from all over the sky. I mean, even on a totally overcast day, it's still bright enough to see, right? That's all diffuse light. And to really know what a solar panel is going to produce, you have to count both.
Okay, so this TMY data from ground stations is the gold standard. But there's a huge catch. These stations are expensive and they're rare. So what on earth do you do for the other 99.9% of the planet that doesn't have a pyranometer sitting on the ground?
Well, you look down from space. The answer comes from our amazing geostationary weather satellites, hanging out about 22,000 miles above us. They give us a way to turn simple pictures of clouds into incredibly precise energy maps for pretty much any spot on the globe. It's this really cool 4-step process. First, the satellite looks at an image and compares it to a stored map of what the ground looks like on a perfectly clear day. That's the albedo. Anything in the picture that wasn't there before
It must be a cloud. Second, it looks at how bright that cloud is to figure out how thick and opaque it is. Third, a computer model calculates the perfect, theoretical amount of sun for that spot if there were no clouds. And finally, in step 4, it just reduces that perfect number based on how thick the cloud is, giving us a really, really accurate estimate of the sunlight that's actually hitting the ground. Pretty amazing.
So we've gone from simple astronomy to ground stations to satellites in space. Why go to all this trouble? Because getting this data right, with this level of precision, unlocks these incredibly powerful ways to design our energy future.
And this is where all that data turns into a powerful tool. You're looking at a contour plot for Phoenix, Arizona, created using that TMY data. It's basically a treasure map for solar panels. The colors instantly show an engineer the sweet spot, the absolute perfect tilt and orientation to squeeze every last drop of energy out of the sun over a full year. It even accounts for things like whether a place tends to have morning fog or afternoon clouds. This is what data-driven design really looks like.
Now, all this complex hourly data often gets boiled down to one super practical number that people in the industry use all the time: peak sun hours. It's just a simple way to talk about the total energy. So if a place gets a total of, say, 6 kilowatt hours of energy per square meter in a day, we just say it gets 6 peak sun hours. It's the ultimate shorthand for comparing locations and doing quick back-of-the-envelope system designs.
So what's the big payoff here? Why does all this precision matter so much? Well, it means you can right-size a system perfectly. No more wasting money on too many panels or being disappointed by too few. It means your financial predictions, your return on investment, are actually reliable. For critical systems with batteries, it's the key to making sure they're dependable day in and day out. And when you zoom out, this kind of precision is exactly what we need to build a smarter, more stable, and more reliable renewable energy grid for all of us.
So we've gone from a simple question to a global system of satellite forecasting. The science of just measuring sunshine has come an incredible distance. It really makes you wonder, as our data gets even more precise and our models get even more powerful, just how much more efficient and how much brighter can our solar future get?